steel beam design. So at the beginning, let me revise some strength of material class. In strength of material class, you learn MC over I. What is this? If I take a beam and if I have some moment, the moment diagram is this. This is my maximum moment. So this beam will bend. If it bends, it will look like this. If I take a small section here, originally it was this rectangular section. After the bending, it will be like this. What means? That means this will be in tension. So here tension, and this will be in compression. So the stress develops here is called bending stress. Same thing, stress develops here is bending stress also. This is compressive, this is tensile. Now we can determine the value of this stress here or here using this equation, MC over I. In steel design class, we do not use sigma, we use F. F means stress in steel design class. So if I rearrange this equation, I can write this way. F equals MC by I by C. This I by C, we can write it as S. S means section modulus. So if I rearrange this equation, it will be F equals M over S. Again, if I rearrange, I will get M equals F times S. Now, what is M? M is my moment, this is my stress, this is my section modulus. Where we will find it? We will find it in our AISC Steel Design Manual, Chapter 1. Chapter 1 includes many geometric properties for many sections. Now, if we do our analysis up to yield point, then this will be yield, and this one we call say nominal capacity. So nominal capacity means theoretical capacity. The capacity of a beam is yield stress times its section modulus. Now, if our section is in linear elastic zone or up to yield point, this equation is valid. What happens if my stress is beyond my yield point? In that case, so when my stress is within linear elastic region, I can write my bending stress equation. No sigma, we use F here. F equals M y I. Y means any distance from neutral axis to my concern point, and if I use C, C means the maximum distance. Okay, if it is linear elastic, my curve is this. If I continue increasing my load, then there will be plastic deformation. Okay, let me draw the curve of stress. Again, it is not stress, it is F strain. If my material is somewhere there, that means above my yield point, then this will not be linear. How it will be? So, then this will be at the beginning. A small portion of my beam will be in plastic zone. If I continue applying my load, then after some times the full portion, again this portion equal, my drawing is not so good here. So whole portion, this one and this one will be in plastic zone. That time what we do? We call the capacity of the moment, plastic moment, F, Y and Z. We do not write S, we write G. What is G? G means plastic section modulus. The value of G for different kinds of section is also available in chapter 1 of your AISC steel design manual. Now, why do we call P? That means plastic moment capacity. So, plastic moment capacity of a beam can be found using this equation, where Fy is yield stress, G is plastic section modulus, and that is the capacity. Now, when you design the beam, what we do? We multiply by stress reduction factor. That means this part becomes our design capacity. Design capacity. So this part is our design capacity, and this is our material capacity from the beam side. So beam can take this. Okay. Next. So to start a design beam, we need to understand something else. That something else is, say my beam is so long. If my beam is so long and it is thin or not so big, what will happen? It might have some lateral torsional buckling. We call LTB, lateral torsional buckling. What is this? If you see your book, you will find better figure. But here in brief, I am telling you that if my beam is so long and if it is laterally unsupported, that means my beam, say here, if I do not support here, it might like have some buckling laterally. So that is a problem for steel beam. Why? Steel beam is very thin but very long. So how to deal with this? Yes, we will learn. Before learning this, we should know some definition of laterally unsupported length or laterally unbraced length. What does it mean? It means that I have a beam. Now this is my span. This is my span. It's not the unsupported length. Unsupported length means if I have something this side and this side, that will prevent my beam to buckle like this. So say if I have a support here, lateral support. So my beam is here, I have a support here or here. So that means this portion cannot move. Only this portion can laterally move. So then my laterally unsupported length. So laterally unsupported length is here to here. So my span is this, but my laterally unsupported length is this. That means at this point I have some lateral support. Okay, so hopefully you understood what is laterally unsupported length. Sometimes we call laterally unbraced length, but that term is not so popular. Laterally unbraced or unsupported, yes, both are okay, but we mainly use laterally unsupported length. And we represent it by LB. Again, it is very important to memorize or understand this symbol LB. LB is the laterally unsupported length. Now let me give you more examples so that you understand better what is LB. If I draw a plan view of a building, say I have a column here, column here, column. Say this is my small building. It has column. This is girder, 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 girder. This is my beam. Now, if I place a slab on top of this reinforced concrete slab or any metal floor, whatever, and then it will tie with a beam, then what will happen? This beam cannot move this way laterally. In that case, what is my LB? Is it this? Is this is my LB? Never, because that is my beam span. Beam span. So this is my beam. Say my load is this. This part is called span. But that is not my laterally unsupported length. Because if I place a deck, here and tie it with my beam, that means continuously, so that my beam cannot move this way. That means my laterally unsupported length here is almost 0, because there is no laterally unsupported length. So it is very important to understand the meaning of LB. LB is laterally unsupported length. It is not the span. For this beam, say this beam is this. My span is, say, who knows, assume 20 feet. Assume 20 feet. Say my load is 2 kg per feet. What is my maximum moment here? Maximum moment, we know that for a simply supported beam with continuous load, my maximum moment is W L square by 8. W is 2 kg per feet. My distance is 20, not distance, span is 20 feet square divided by 8. Here we are not using 0, because that is the span, and this is LB, laterally unsupported. That means this beam has continuous lateral support. It cannot buckle like this. So hopefully you understood what is the meaning of span and what is the meaning of LB. LB is very important. So next I will tell you why LB is very important. Okay, now why LB is very important? Because by calculating or knowing the LB, we know whether there will be lateral torsion buckling or no. So if my LB is 0, that means no lateral buckling. In that case, my capacity of the beam is P, for PMP is P Fy 0. So if my LB is 0, my capacity is this. Now this whole value we can take it, we can grab it from table somewhere in chapter 3. So in our AISC manuals table, somewhere in chapter 3 we can find this value. Now, for how much unsupported length this value is valid? That means, say my beam is 20 feet. Can I have my lateral support every 5 feet or every 4 feet like this? So AISC gave us some specification. If our LB is less than LP, now LP is another length. We can calculate it using empirical equation, or again we can read this value from a table. If it is less than this, then still this equation is valid, the capacity of moment. If our LB is in between other two values, this is another length. This is called LR. That means when my beam is slender, so long. So when my beam is in between this, the capacity T will decrease. And what will be the capacity? The capacity will be, I forgot it. Okay, I'll take it from the book. But again, make sure that you are understanding that the unsupported length is important. If unsupported length or laterally unsupported length is 0 or less than this number, this equation is valid. If it is more than LP but less than LR, the capacity is a different equation. How can I find it? 1 minute. Yes, in that case, for this this case. So for this case, my capacity is Mn Cv Pmp minus Pmp minus 0.7 Fy is. Now sometimes, not sometimes, most of the time we write not S, as X. Why X? Because beam bends mainly about X axis. LP did I write correct? Yes. Now what happens if my unsupported length is more than LP but less than LR? Now what is the value of LP LR? I am telling it later, but just to tell the capacity earlier. And if it is in between, then my capacity is calculated using this equation, and that must be less than my this value. Now what is this? Cv, again a moment gradient factor. We will talk about how to find this. So this one we can directly grab it from AIC manual chapter 3. This portion, that means this portion, we can also grab it as phi pf. This portion, in short, we call phi pf. We can also grab it from our AIC manual chapter 3. Then LB is our unsupported length. LP is our empirical length, below which we call, so LP we call a unsupported length below which inelastic lateral torsional buckling occurs. If it is more than this, inelastic torsional buckling occurs. After this we call elastic lateral torsional buckling occurs. Okay, so hopefully you understood. If my LP is less than LP or 0, whatever, because 0 means it is less than this, capacity is this. If our length is in between these two values, our capacity is this. How can we find it? Very easy. This portion from a table, from a figure, this portion from AIC manual, whole portion is phi pf from AIC manual. LB is our unsupported length. LP we can also grab it from this book, or we can calculate. Now other case. If our length is LB is exactly equal LR. If LB is exactly equal LR, our capacity is phi 0.7 Fy S. That is this portion. So if LB is exactly equal to LR, our capacity is this. Now what about if LB is more than LR? If LB is greater than LR, there is another equation. That equation I am writing somewhere up. So if LB is more than LR, that equation I am writing here. LB greater than LR. In that case, my capacity is FCR SX. It looks very simple, but again, FCR, it is used. Okay, let me write it down, or it is in your book also. Let me clean it a little bit. Good. Where, how can I find FCR? My FCR will be CB Y square E LP RTS square then square root 1 plus 0.078 z c s x h naught. I need more space, so I clear here. Then LB RTS square. Now, if our LB is more than LR, this is the equation we can use to find our capacity of the beam. Now, all the terms RTS, it has no technical name. This one is given J, C, RTS, H naught, everything. It is geometric properties. We can find all these values in AICM chapter 1. Chapter 1 includes all kinds of geometric properties. So we can find all these J, C, RTS, SS, H naught, everything we can find there. CB. To find CB, we can use a table, and that table looks like this kind of table. You can see different kinds of beam. This table is in your book, in your AISC manual. It is in FE reference handbook also. Okay, now let us talk about CB and what is LP, what is LR. So before going there, make sure you understood. Based on your unsupported length, the capacity of a beam changes. If LB is equal or less than LP, capacity is this, phi MP. You can read phi MP directly from your AIC manual, or we can calculate using this equation. Where phi is typically 0.9, at this moment it changes. Equal yield stress of your material, this is section modulus, plastic section modulus, you can find it from AIC manual. If LB in between, then the equation is this. The whole part must be less than your PMP, which makes sense. Now CB, you can read it from a graph figure. This one from AIC manual. Whole part PBF from your AISC manual. Then this part your LB. This is your LB. So if LB equals LR, this is our capacity. If LB is more than LR, this is our capacity. How to find FCR? This equation. Most of the things you can find it in your AIC manual chapter 1, or we can directly read this from AIC manual chapter 3. We'll go. So now we will talk about 3 parameter. So now we will talk about CB, LP, LR. So what is CP? CP is CB or CP? B is right. What is CB? It is called moment gradient factor. How to calculate? Again, you do not need to calculate it. You can directly read a figure. For example, you can calculate. In your book there is a equation. Say start with equation, although you do not need to use equation. So 12.5 A max, then 2.5 A max plus 3 MA plus 4 MB plus 3 MC. Then there is a factor. Okay. Forget LP or L. How to find it? Say you have a beam here, there is a lateral support here. Now if the beam has load this kind, or make it simple, this kind of load. That means whenever there is a load, there is a lateral support. So for this beam, if I draw the moment diagram, it is this straight line. So we will consider it in the unsupported length. This is our unsupported length. So in this portion, M max is this value. M max. MA beginning 1/4. That means whatever the length, 1/4. So this will be L by 4. Say this is my L. Say it is L. Then the moment here is called MA. And then the moment at next portion is center line of this. That means this one is L2. This moment is called MP. And then 3/4. Somewhere here, this is MC. So MA, MB, MC, and it is 3/4 L. Yes, 3/4. So if it is L or LB, better to write LB. That you can write, memorize easily. So whatever your LB, MA is the moment at 1/4, MB is moment at the middle, MC is the moment at 3/4 of that length. Max is your maximum moment. And then what is RM? RM is a symmetric factor. You can read it from book. It is 1 for I type beam. Most of our beam is W is I. So for double section is typically 1. Now it is a long story. Make long story short. There is a figure. How to read figure? Say if you have a beam here, one reaction here, there is a load here, but no lateral support. In that case, what is your CV? CV is 1. Same beam, say my load is here, but this time I provide a lateral support here. In that case, my CV is 1.67 for both sides. CV is 1.67. Say another kind of beam, reaction here. Say my one load here. We call it third one loading. For this case, my CV is 1.14. So this way, you can see the table. There are different kinds of beam and different kinds of loading and different kinds of lateral support. Based on this, you can read your CV value. But to let you know, it is always conservative to use CV1. So when you do not know or in your real life what to do, use CV1. In your FE exam, this table or this figure is provided. So make sure that you are familiar with this figure. So that is the story about CV. Other story about other story is about LP, LR. So LP, LR. What is LP? LP is the unsupported length above which inelastic lateral torsional buckling occurs. So how to find LP? Not so difficult. 1.76 RY, then EY, 8Y. What is RY? Minimum radius of gyration or radius of gyration about y-axis. E means modulus of elasticity, F means yield stress, is a constant. And what is LR? Very big equation. 1.5 E 0.7 Fy C Sx H0 again some. Yeah, there is something more. Now, okay, let me write it down, because sometimes I become so lazy, but I should not be. So again, you should not be lazy too. Case 0.7 Fy Sx H0 E Jc, that is square here. Yeah, again to tell you most of the parameter like Sx, H0, C, Z, J, C, S0, everything you can find in chapter 1 of your AISC manual. E is always known for its still 29,000 Ks or 210 gigapascal. Phi is your material yield strength or stress. It can be found in chapter 2 of your AISC manual. So these are the two equations you can use to find LP. Now to make life easy, this value you can read it directly from your AISC manual chapter 3. So this value you do not need to calculate. You can find it in your AISC manual as long as your FY matches. Okay, now where? Let me show you the manual. Say for example, chapter 3, if I open a table, say table 3.6, any section, say randomly I found a section, say W24, or it is page number, take a popular section. Increasing that way, not decreasing. Say W1240. Well, yes, W1240. It is page number 3-68. 3-68, table 3-6. W12, say 40. So you can see W1240. Now below this you can find very small number. The second one, PMPX. Or PMP. What is the value of this for W40? PMP is, if I can read, yes, 1710, 1710. Unit is cube feet. That means if it is a W1240 section and if your unsupported length is less than LP, the capacity is 1710 cube feet. Now what is my answer? This is a we found. Okay, let me write it down so that you can follow. So what we are doing here, AISC manual, and it is edition number 15th edition. I am reading page number 368, table 3-6 for W1240 section. My PMP is 1710 feet. What else can I read from this table? Say whatever I need, I will read. I can read PMPR. Next value 210 cube feet. I can read below this is PBF. PB for this beam is 5.54. If I am reading right, 5.54. I can do LPLR. LP 6.85. LP 6.85 feet. LR 21.1 feet. 1 feet. I can also read G. Gx is almost 57 inch to the power 3. So you can see that most of the value we need to design a beam, it's available in this book. So for different kinds of section we can use it. Now let us do an example very quickly. So we will use this section. Say this is our beam. I have this kind of load uniformly distributed. Say load is 2 kg per feet. my span is say 20 feet. Lateral support say only at the middle. Only at the middle, my lateral support. Then is W1240 good for this one. Say my beam uniformly distributed load 2 kPa moment span is 20, lateral support is there. So this is my laterally unsupported length. Is a 1240 section good for this beam or not? What to do? Yeah, one thing I forgot is that before starting or designing it, we should say whether the thickness is good or not. We discussed it while designing compression that this section must be compact or non-compact. What does it mean? That is the thickness to width ratio should have some minimum value so that it doesn't buckle locally in planes or in wave. But now we are not doing it. Maybe in another time we will discuss about that. Now we will design this beam. Is this beam or is this section good for this beam? Okay, find it. First of all, what is my maximum moment here? Now this load must be factored. This problem did not tell us. Okay, let me. Okay, say assume this is our factored load, WU. What does WU is? Factored load. Okay, then what is my moment? My factored moment is WU L square by 8. So W is 2 kPa, L is 20 feet, 8. Again, to remind you, the load must be factored. We saw these are very old history. So 220 square divided by 8, very round number. I got 100 kp feet. 100 kp feet. So that is my moment, actual moment. Then what is the capacity? We have to find the capacity of this beam. Now, okay, I'm not reading it because we need it. What is my LB, laterally unsupported length? That is 20 or no? It is not 20. My lateral support is here, so unsupported length is only 10. What is my L? What is my LP? From the AIC manual, I found my LP somewhere here, 6.85. What is my LR? 21. LR 21. So where my beam is? My beam is in between these two. So bigger than LP but less than LR. So my beam is in between these two. So what is my capacity equation? If I write it here, my capacity equation, can I remember it? If I can remember correctly, it is MN, there are CP and some value here MP minus P. Simply this portion we can write PF LP minus LP. Okay, to make it clean, or even let me make more space. So this is the capacity question when my beam is in between. Now this time I wrote it short because it's a big term, and that big term is PPM. We can read it from table 5.5. Now the whole value must be less than this value. Why? Because this is the capacity when my beam is equal or less than this. Oh, now what is the value of CV? We have to read from the table. Say I have a book, and which case uniformly distributed load, lateral support at the middle. So if I read your book, uniformly distributed load at the middle, it looks 1.3. You can see uniformly distributed load, there is a lateral support x means lateral support, sweep is 1.3. So we got 1.3. What is this portion? This portion is 17, 10. What's my beam factor? 5.54. Let me fill this portion also. Then what is my LB? My LB is 10 feet because unsupported at the middle. What is my LP? 6.85. How much did I get? 1710 minus 5.54, then 10 minus 6.58. Did I make any mistake? Yes. 1710 minus 5.54 times 10 feet minus 6.58. I got, okay, times 1.3. I got 2198. 2198. So 2198 keep feet. So my capacity of beam is 2198 keep. Oh, this value must be less than this. That means whole thing must be less than empty. 1710. It looks to me that I made a mistake somewhere because it is very high. Yeah, typically these values should be less than this most of the cases, but as I got more, I should check one more time. But it is not that it cannot be more than this, it can be, yes. Okay, let me check again. Everything, so CV is correct, 17 is correct, 5.54. Let me check whether it is 5.54 or no. A beam factor PBF is 5.54. Again 1710 minus 5.54 times 10 minus 6.85. 1694. Keep it. Keeps. Yes, I do not think we made any mistake. So 20. This time I got 2200. Okay, whatever it is, maybe slight mistake in my calculator. So what you will learn here, so the capacity of this beam should not be this one, should be this one, lower one, because this part cannot exceed this. So what is the capacity of my beam? 1710. What is my actual moment in this beam? 100 keep feet. Again to check. 2 L square 20 feet. That means 400. It is right. 100 keep feet. So my actual moment is 100 keep feet. My beam can take 1700 keep feet. So my beam is good. Okay, so we finished on example. The same example. If I extend it, say now I am assuming that my lateral support. Okay, do not confuse. So I am doing in a second example. What is the second example? Now I am changing. Say my continuous support is all around continuous support. That means there is a slab on top of this. That slab will prevent the buckling. Then what will be the change? The number of change will be, first of all, then what will be our new B? 0. So that means LB less than LB. What is our capacity? Capacity is just this portion or this portion. So I will delete everything. If my lateral support is now continuous, my LP is 0, LP is less than this. What is my capacity? Capacity is LP. Really. What is the value? From the table we found 1700. So that is my capacity. What is my actual moment? 100 kPa. So this beam is good. Now in AP exam they might ask you what is the capacity of this beam. In that case your answer is this one. Now AP exam doesn't, in AP exam you cannot use this book, but some pages, few pages of this are available to you. So before going to exam you can see that also. So today we will stop here, but make sure revise this what we learn. We learn how to design a steel beam. What to do? First we should say what is our armrest length. Very important. What is our armrest length? If it is 0 or what is the value? We should set that. Because based on my armrest length, my capacity equation changes. Okay, so check your armrest length and then compare it with LP and LR where you are. Based on that, your capacity equation changes. And once you know that, then find all other values, insert it and solve it. Simple. So we will stop here, read your book, practice more, and we will keep on discussing.